Okay, thank you. So my name is Sudhendu Tiwari. So I'm working with Dr. Agnihotri. So I'm going to present estimation of crack resistance curves and crack paths in ceramic
Ciao
polymer
Gabriele,
composites
ciao.
Aspetta che tolgo la voce.
with
Togli la voce dalla pentola, c'è ancora
Che cosa?
penso che c'è ancora la voce, il
I'm
volume
hearing some noise.
sul convegno acceso.
Francesco, please can you mute your microphone?
Yeah, thank you. So I'm presenting estimation of crack resistance curves and crack paths in ceramic polymer composites with a nacre like lamellar and brick mortar structure. So starting with the motivation, so here are the few examples which includes bone, bamboo, and a few kinds of mollusk cell. So all these features have a very light in weight, has have high strength and high toughness. So what is the key issue? So I'm here with example I'm showing here. So this is a general scaling law. Let me. So if we want to make a material stronger, then it becomes brittle. So in engineering sense, if we see here in stress strain diagram, so if a material is hard, then the area under this curve will be low, and thus it will have a low toughness. And conversely, if a material has a high deformability, means high percentage of elongation, then the area under curve will have a much high value. So it will be tough, but the strength will be low. So yes, so there is a paper by Sir Rishi, that is the conflict between strength and toughness. So the problem is, can we make some materials which are stronger as well as tougher? So what is the solution? What is the possible strategy? So yes, so there is a nature inspired solution. So if we see this SV chart presented here, so this the inner layer basically is known as nacre, and it is composed of mainly 95% of brittle ceramic and only 5% of organic things. That is a biological protein. So if we compare here the toughness values, so this calcite has only of J value, toughness value is 0.001 kilojoule per meter square. But it when it combines in such a nice way, we will see in the next slides. So its toughness is amplified by a huge amount, by 1,000 times, and it possesses now 1 kilojoule per meter square. So what is answer is basically that is this what are the composition and what is the structure. So yeah, so if you see, the composition is biological protein, which is only 5%, and 95% is it is a calcium carbonate, just chalk like things, but yeah, it is a stable one which is known as aragonite. And these two combination are basically they are arranged in such a nice way which looks like so this is at a major scale. So at major scale it looks like a just brick mortar like structure as we see in a wall of house. But at a micro scale, if we see, so these platelets have dovetail kind of feature. So under loading condition, what happens? They provide external locking. And if somehow if there is a generation of crack, so crack will travel a longer path, giving some kind of punctuosity. So further, if we amplify these, so I made these schematics which represent a brick mortar, something like a structure. So these platelets, if we see, so these platelets have around, so this is will be in the order of micron, and these platelets has a nano disparities in between, so it also resists by frictional sliding, and in between these two platelets there are organic glue. So thickness of these organic glue is in the range of a few nanometers, that is in the range of 20 to 25 nanometers. So thus due to presence of these kind of feature, that is presence of these organic glue, presence of nanoasperities, presence of dovetail kind of features at various length scale, means ranging from nanoscale to the at micro scale, are the main things which amplifies both its strength and toughness. So now the question is, how artificially can we produce this kind of material? So yes, one feasible strategy is a freeze casting method. So in freeze casting method, what I have done is I have taken alumina powder, which is a ceramic, and it has average size around zero point 0.6 micron. Then I have made a alumina suspension, means aqueous suspension, by keeping 20 volume percent only alumina and rest is water, and added some organic additives as well as some kind of dispersant. I have used Dolapix CE64. So after making this suspension, so this is a typical PT diagram, pressure temperature diagram. So I'm showing here. So alumina suspension is poured in a previously prepared mold, and the base is actually the base is cooled by supplying a liquid nitrogen. So in my study, I have maintained a temperature around minus 30 degrees centigrade, and this one explain the freezing. So during freezing, what happens? Ice nucleate at the bottom, and it grows something like this. So this is a preferential solidification of water. So ice grows from bottom to top, and as it grows, it repels these ceramic particles. So ceramic particle separates, and ice grows from bottom to top. So by doing so, we get a frozen scaffold. Now this frozen scaffold is processed to a sublimation process. So under I think I have done at zero point zero 0.01 millibar, and temperature was minus 55 degrees centigrade. And during this event, what happens? This ice directly converted into vapor. So we left with this these kind of things, pillars of ceramic scaffold. So this is basically called green scaffold, which is very weak, because I have added few very only 2 weight % of organic binder, which is I have used polyvinyl alcohol PVA. So it is very weak. So I have sintered then at 1450 degrees centigrade, and then I have seen the microstructure which look like this. So we can see here this is a porous scaffold. But what happened actually, if we look at these boundaries, so these are lamellar structure, but there are many monodomain structures. So they are not aligned as we have seen in the case of nacre. So at the next level, what I did, I have modified, uh, I have modified the operators. So the base is now modified by a copper base and an inversion of another material, that is PDMS. So this is a polymer I have placed over the copper plate to induce an additional temperature gradient. So here in this case, a temperature gradient is only from bottom to top. Now in this case, what happens? The temperature gradient is split. Although our temperature field is singular, no doubt, but with the addition of this PDMS base, the temperature field will be split into two parts. Now what happens? These ice grows vertically as well as horizontally. So after processing by this method, this is basically known as bidirectional freezing. So we have obtained a very long range aligned zone, we can see here. So now in this study, I have used the ceramic scaffold using bidirectional freeze casting technique only. So this is one of, I have captured few pictures as a function of time. So this is the, so in the right direction, it shows the progress of freezing. So this is the case of unidirectional, the top one. So in this case, the ice fronts parallelly grow. But in case of bidirectional freezing, so this is a PDMS gauge. So this point cool faster than this point because PDMS is insulator and this one is copper wedge. So ice fronts will be something maybe like this. So there is a observation of wavy profile which further confirms this kind of nucleation and ice growth. Now, so this is what a nice picture I have taken. The scaffold are taken from obtained from bidirectional freeze casting. Now, using this, I have processed two kind of composites. One is lamellar composite, and another is brick mortar composite. So processing is are different. So after obtaining this ceramic scaffold, I have directly infiltrated using vacuum technique. So I have infiltrated with epoxy and then post cured at 80 degrees centigrade for 4 hours. So now this is called a lamellar composite. In second strategy, what I did, I inflated it with wax to preserve the lamella, and then actually I have pressed it at 40 MPa and at 80 degrees centigrade. So 80 degrees centigrade I have decided because around above 60 to 80 degrees centigrade, wax just melt and becomes liquid state. So during applied pressure, it flows out and the lamella is also conserved. So after pressing, we get this densified scaffold, and again this densified scaffold is sintered at 40 or 50 degrees centigrade, and after sintering, again I have inflated epoxy and then post cured at 80 degrees centigrade for 4 hours. So these two kind of composites. So this is if we see this picture. So so this looks like something a nacre like features. So these are the places which are well aligned. Yeah. So what I did in order to account the weight percent of alumina phase and epoxy phase, so I have just a bond test. I have taken few samples and put them at 600 degrees centigrade. So I got alumina weight percent in this case is around 60 weight percent. In this case, it is 70 weight percent. So this composite is basically yeah, I'm saying it is a brick mortar composite. This is now I did a fracture toughness measurement. Basically, I have evaluated a JR curve. So for that, I have used ASTM E1820, and these are the well standard procedure to measure the JR curve measurement. And this is the representative SENV sample. So here we can see I have first made a notch, and then by slightly by pressing a razor blade, I have created this crack. So I have calculated a J integral. So J integral, it is defined as the sum of J elastic part and J plastic part. And we know this is the standard procedure. So I'm leaving this. So after calculating iterating at each loading and unloading stage, we can calculate also the crack growth using compliance method. Now, so this is the result what I got. So this is the force and load light displacement. So the red one is for brick mortar. So this is a CNB test results, and this black one is for lamellar composite. So so here I have designed experiments such that at each step, actually I have designed for 15 micron of displacement. There is an unloading of 10% of unloading. So following the ASTM standard, and before reaching, it must have at least 7 load unload. So yeah, so there is at more than 7. Now we have to decide. It is a very difficult to monitor the crack grow using visual eyes. So it is very difficult to pick a point at which point the crack is about to grow. So yeah, so I have taken first non-linearity. So there are various we to account that. So I have taken the first point which is a non-linear, and this becomes the critical load. Using this point, I recursively using following the ASTM standard, I have calculated J and also extension in crack length. What I have found that so J versus the delta A curve is too near for lamellar composite. So black one is for lamellar composite, and the red one is for brick mortar composite. Here we see so J is higher. J is higher for lamellar composite. So when I have evaluated this, then further I have evaluated this amount. What is the work of fracture? So area under the curve. So area under the curve is higher for this black one till the fracture point. So work of fracture is even higher for lamellar composite, and for brick mortar composite it is slightly less. So, this is the limit. So these points are not a valid point because the 75 crack extension is only allowed up to 75% of the ligament length. So in my case, ligament length is around 1.5, so it gives around 0.375. So valid reason is only this one. So maximum J max value for lamellar composite is 2 kilojoule per meter square, while for a brick mortar composite it is reduced by 0.2 kilojoule per meter square. Yes, so this is untested specimen, SEM micrograph of untested specimen. So after testing, I have taken the SEM micrograph. So here we can see even the crack. The crack is how it is growing. In the case of brick mortar composite, the crack growth was observed something like this. Yeah, so in this case, we have seen there are some chunks of epoxy which comes out because of larger pores. So during finishing, I could not manage. I mean, such that. So these are not the through the thickness because I have now seen. I have not put this into the slides. I have taken the fracture surfaces. So these are the not the through the thickness. So this is just a surface defects during polishing. Some epoxy of chunks comes out.
Excuse me, Sudhendu, you have 1 minute left.
Okay. So in conclusion, is a bidirectional freeze casting route is a feasible strategy to fabricate nacre-like composites. So even a mode 1 stress intensity factor is higher for brick mortar composites than lamellar, but work of fracture and Jmax is higher for lamellar kind of composite.